Hey there! So last time we talked about this Parquet format. That is pretty cool, it's way better than CSV, but it's not ideal. No, that's even a better format that you can use that brings reliability to our data lakes. That's the format which made this data lakehouse concept possible. And namely, this is Delta Lake. So the topic for today is Delta Lake. So let's get started. Now, Delta Lake. I know it sounds similar to Data Lake, but these are two different things. So please don't confuse them. So actually, let me start noting the most important stuff about Delta Lake. So Delta Lake. That's the ultimate file format, or maybe I should say storage format. So basically, what is Delta Lake? And guys, please don't confuse it with Data Lake. Both of them sound similar, but these are two different things. So Data Lake, the thing on the right, is only our storage layer. And in case of Azure, we would use storage account with this hierarchical option enabled, in which we would store files like CSVs, Parquet, XMLs, and so on. Delta Lake, the one on the left, is just a storage format like CSV or Parquet that adds super cool features to our data. So basically, what is Delta Lake? And simply, it's just yet another open source storage format. So it's open source storage format. So you can think of it like something similar to CSV or Parquet. That's what Delta Lake is. It's just a storage format. And again, like in case of Parquet, it's open source, which means that it is being developed by community. There is no single company that is allowed to use this format. No. And actually, this Delta Lake format, it has been widely adopted by various tools and by various services. For example, if you think about the default file format that Databricks uses to save data, well, that's Delta Lake. Likewise, what file format is used by Microsoft Fabric? Again, it's Delta Lake, simply because it is so cool. Now, under the hood, Delta Lake, it's just Parquet files, so it uses Parquet, the same format that we discussed last time, and it adds transactional log on top of it. And that's this super cool thing that adds additional features to Parquet. And this transaction log, it is saved just as JSON files. So yet another file format that you should be already familiar with. All right, so let's jump to Azure Databricks and let's create some Delta Lake files, some Delta Lake dataset to see how it looks like. So I'm in Azure portal connected to my Azure Databricks instance. And again, at this moment, please don't focus at the Databricks itself. We will have separate sessions just about Databricks. For now, just pay attention to the things we can do when it comes to Delta Lake. So in our first command, what I'm doing is that I'm creating a table, a data set called people, this one, that will be saved as Delta Lake. This using Delta clause is the one that indicates how we would like to save our data. This table, this dataset will be saved on my data lake on my storage account. And basically, to populate this dataset with data, I will simply read my Parquet files that I store in a data lake. So let me execute it. And now you should see that actually this command that I'm running, it's a SQL command. It uses SQL-like syntax, which should give you a hint that actually, in case of Databricks, in case of Delta, we can use SQL. So if you have SQL background, just like me, and you can use SQL very fluently, then it should be quite easy for you to transition to use Databricks with this SQL language. Now, this command will execute for 30 seconds or so. So in the meantime, we can jump into my data lake, again, storage account. So that's my storage account. And here we've just created this table, this data set. So let me refresh a list of directories. And yes, there is this directory called Delta, because that's how we defined our table that we want to be stored in this particular directory. Now, if we jump into this folder, you should see that my data was actually written as two Parquet files. So that's the format that we already know. But what is very important in case of Delta Lake is this Delta log directory that stores our transaction log. And I told you that it uses JSON files. So let's take a look into our transactional log. And here you can see those JSON files. Right now we've got only a single JSON file. And basically every JSON, it represents new version of our data, new commit that was made by our queries. And if we take a look into the file, it's just a regular JSON. You would see that actually our dataset, our table, it consists of two files. And in this JSON log, we can see exactly which files, which data files, which Parquet files should be used to read the contents of our table. And now, it might be a little bit confusing for you that I'm using a word table, because tables are used basically for databases. In this case, please be aware that we don't have a separate database. No. All data is saved in a data lake, in a storage account, just as Parquet files with this transaction log, which creates this Delta format. And Databricks is used just as an interface we could use to query our data. Now, what's also quite cool inside this transaction log is that for every file that creates our data, for every Parquet file, we've got various statistics. Like, for example, we've got min and max values for every column from every Parquet file. And you will see in a second that this information is quite useful when we want to skip reading some files just to make our queries faster. All right, so let's get back to our Databricks instance. Let me show you that actually I can query my people table using SQL syntax, but again, there is no database under the hood. There is no SQL server. This command is executed against our data lake that stores data as Delta format. And yes, we can see that our table contains those employee data like ID, first name, last name, gender, birth date, and so on. All right, cool. So let's start to modify our data and see how it affects our data stored on a data lake. So here I've got a very simple update statement, again, a SQL query executed against files, in case of which I'm updating name of every row to Piotr, where existing name is set to Penny. So let me execute this query, and it actually, let me stop for a second, take a look at the command here. So Databricks took a look at the transaction log, at the files that consist our data, and at this moment we had 2 Parquet files, and it decided that it had to make changes into files, because rows that meet this where first name equal to Penny predicate, they are most likely stored in both files. So actually both files have to be rewritten. All right, so we made this update, it succeeded. So let's take a look at our data. So let me refresh the contents of the transaction log, and we can see that we've got a new version of our data, new commit was registered. And in this commit, we can see that actually 2 data files, 2 Parquet files that were used previously are no longer a part of our dataset, because they shouldn't be considered a current version of our data. And instead, what we have are 2 new files with different names that contain updated data, right? So let's check the data files, how it looks like. And indeed, right now we've got 4 Parquet files. 2 of them, just by looking at this modified date, so those 2 were the original files before the update, and those remaining 2, this one and this one, they represent the current version of our dataset, because they contain the data in which first name was updated to Piotr. But the old data is also there. All right, so let's make yet another change. This time, let's make it very selective. So in this case, I am again updating first name to Andrew, but I'm targeting a single row, the one that has ID equal to 1, 2, 3, 4. So let me execute it. And this time, this time, take a look that only a single file had to be updated and rewritten. Why? Because again, Databricks, based on the transaction log, was able to decide that this row with ID 1, 2, 3, 4 is stored in a single file. So only a single file has to be modified. And again, this operation succeeded. So let's take a look at our data stored in a data lake. So we've got this time 5 files, 5 data files, 5 Parquet files, because only one was modified. And if we take a look at our transaction log, we can see yet another version, the third one that was created. And here we should see that actually one of the files that was used to as a previous version is no longer valid, it's obsolete, and instead we should use this particular file, because that's the one that contains our change. But please note that still all of those historical data is available here in our directory on a data lake. And it's a very cool feature, because soon I will show you how we can use this historical data. But it also means that whenever we are reading delta tables, delta datasets, we cannot just read a specific file like this one, because it might contain obsolete data. that are no longer valid. No. Our query should target specific directory. And it would be a query engine responsibility to go into the data log, read it, and understand which data files should be actually read. So based on the data log, maybe in our case, this file and this file would have to be read, depending on the context. But basically, that's how transaction log works. Every operation, every modification that we do results in creating new JSON file, new commit in our transaction log, and new versions of our data file. All right, but so what? What's the point of doing this? At this moment, I can see only a drawback, as if we take a look at our folder with data, you can see that each of those files has a size. So we are creating copies of our data, and we'll have to pay for them, because we pay for the amount of storage we use in case of storage accounts. So what's the point of storing those historical versions of our data? Why just not update them in place? And that's what I would like to explain. So basically, Delta Lake, it gives us ACID guarantees, something that we didn't have in case of Parquet. So ACID guarantees. And this is huge, because that's something that we have in databases, like in SQL Server. But in case of Parquet files, CSV files, we don't. They are just files. And if you are not sure what ACID means, so let me explain it. So A, it stands for atomicity. Atomicity. And it basically means that our transaction, our operation that we execute against our data, it either completes successfully as a whole, or if some issue was encountered down the road, that it is rolled back completely. So the final state of our data is as if it never happened. So either it succeeds completely, or it didn't happen, which is extremely important in when we work with data, because we don't want to have only a part of our operation that was written somewhere. No, either everything succeeds, or it is rolled back. And you might think, all right, but how does it translate to our files? Well, simply in case of data lakes, most likely we will be working with multiple files per dataset. In the previous episode, when I was showing those Parquet files, we had only a single Parquet file, but it's rather an exception, not a rule. Usually, we would have multiple files per dataset. And basically, there are two main reasons why it happens. So first of all, we have parallelism. So please remember that we are working with big data, huge amounts of data. And to make it faster, to make processing faster, we use tools that are able to spread the workload between multiple worker nodes, each of which would have its own part of the work to be completed. And each of those worker nodes might end up writing to its own file. So basically we would have multiple files created that together would create our dataset. And basically that's what we have here in the case of our file. Initially, we had our people dataset written as two Parquet files. So it was already distributed into two files. The second reason we might have multiple files is partitioning. So partitioning. And it is used when we want to explicitly split our data into files based on some value, based on some column, to make basically our queries faster. So let's say that we have on a data lake, our directory with some data. So let me call it some table folder, inside which we would have, first of all, our delta log. So this is this transactional log. And then we might want to explicitly partition our data. So physically split it into multiple directories based on some column. For example, we might want to split it on country column. So we might have a directory called country equal US. And then under this directory, we would have multiple files, multiple Parquet files. And each of those files would contain only rows for which country is equal to US. Then we might have another partition, let's say for country equal to PL. And again, under this folder, we would have yet another set of Parquet files. This time, each of our rows would have a country set to PL, and so on. So you can already see that our dataset, our tables, will be most likely split into multiple files, either because of parallelism or partitioning. And this atomicity, in this case, is extremely important, because let's imagine a case in which we write a query that updates the whole table. So physically, updates has to be made to every file. Let's say we've got 100 files, and our query engine started to rewrite, let's say 20 files, and then it fails. Something bad happens. Our cluster dies. So at this moment, 20 files were rewritten, were updated, and 80 files weren't. So our data is not in a consistent state. It's in a mid-transaction state. And that's very bad, because it would corrupt our data. In case of Parquet, this might happen. And then, well, we've got bad luck. In case of Delta Lakes, this can't happen because we've got this atomicity guarantee. So basically it works that changes to our Parquet files, to our data files, alright, they are made, but only after all changes have been written, only then a new commit is written to the transaction log. So, okay, if in the middle of the process something bad happens, no problem. We would have those additional Parquet files, but there won't be any commit in the log. So those files would be just ignored, those new Parquet files. So always our data would be consistent, and that's very, very important. All right, so it was A for atomicity. Then we've got C for consistency. Consistency. And again, consistency is all about making sure that integrity of our data is maintained at all times. So we can think of it like this. So if we've got our data in state 1, whatever it is, and we want to migrate it to state 2, let's say we want to update some rows, or maybe want to insert new rows, this consistency guarantee means that every time in every state our data will be consistent. Integrity of it will be preserved. So if you have some constraints defined that tells how data should look like, it is guaranteed that all of those constraints will not be violated. So data will be consistent. And it is related to the next guarantee, A, for isolation. And this one is about concurrency. How different queries that are executed at the same time, how they impact each other. Will there be some conflicts or not? And in general, there are two ways isolation can be handled. One of them is pessimistic model, in case of which it is assumed that there will be conflicts. So if I'm reading some row, then for sure someone else would like to modify this row at the same time. So the engine has to log this resource, and it won't prevent the other process to modify it at the same time. And this model is used by default in, for example, SQL Server. The opposite is optimistic concurrency, in the case of which we say, all right, there is a very low chance that our transactions will conflict with each other. So there is no point in locking the resources. And actually, Delta Lake uses this optimistic model, and it is implemented in two ways. For read transactions, it uses snapshot isolation, which means that every transaction that just is reading a data, it will see a consistent state of our data from the time it started the reading process. So to give you an example, so let's say I'm running a transaction that has to read all files from our dataset, 100 files. And at the same time, there is some other transaction that modifies the same file, the same set of files. And actually those two transactions, they can run at the same time because I, as the reader, I have a snapshot of my data. So based on the transaction log, I know how the data looked like at the time when I started reading the data. So it is completely fine that some other process is overwriting the data, is modifying them, because I still have access to my version that was valid at the time when I started reading. So it simply means that readers do not block writers, which is pretty cool. Now, in case of concurrent writes, so in case of two transactions that would like to write at the same time, again, we use this optimistic model, and it is implemented in the following way. So first, the write transaction reads the current state of our data, again, based on log. Then it makes any updates that are necessary, so it creates those new Parquet files. And then finally, before committing those changes, which means that before writing new entry, new commit to the transaction log, it checks if there were any changes done in the meantime by someone else that might conflict with its changes. If yes, then transaction will be rolled back. If not, it will be committed. So it means that in optimistic model, there might be some conflicts, and there are some techniques that we can use to minimize the number of conflicts, but that's a topic for a different session. But on the other hand, there are some operations that won't conflict at all. For example, if two transactions would like to append new data, add new rows to a table, well, they can be executed at the same time. because they are just adding new rows to our data. So they won't conflict at all. So that was isolation. And the last one is D. And D stands for durability. And again, durability means that the change, the transaction that was committed to the log, it has to be persisted, no matter what. It cannot just disappear. And simply because we store our data on a data lake, on Azure storage account, we inherit its guarantees about durability. So you should already remember about those LRS, ZRS, and GRS redundancy options that guarantee that our data is available even in the case of some hardware issue or data center issue. So basically, to summarize, with Delta Lake, we've got those ACID guarantees, something that was missing in the early implementations of data lakes. And we want to have these ACID guarantees when we work with data. So that's a very cool thing of Delta Lakes. All right, but that's not it. You should remember that when we make changes to our data, all of them are recorded as various commits in the transaction log. And actually, we could use this to audit the history of our data. So let me show you how it looks like. So let's go back to Databricks, and I will use command describe history. And let me execute this command. And here you should see that Databricks was able to read a transaction log of our people dataset, and actually it detected 3 transactions, 3 commits that were made on our data. So we've got 3 versions of our data recorded, and we can see exactly when given change happened, who made the change, what operation was made, and some parameters if there were any. So for example, we can see that it was me who made the update. When I was updating a first name, that was equal to Penny. So we've got these auditing possibilities just out of the box, just because every transaction is saved in the log. Every commit is in the log. So we can see who did what, basically. And actually, it's pretty cool, because that's the first place you would check if you would notice that something was messed up with your data. And here, based on the history of our table, you could clearly see who did what. So we've got this basic auditing available. Now, the next cool feature we have with Delta is time traveling. I know, fancy name, but it simply means that, well, we can see previous versions of our data, previous state of our data. So again, let's take a look at our data. So you should see that actually we store those 5 Parquet files. And some of them, they represent the state of the data from the past. And we have our transaction log, in which we've got every commit recorded. And each of those commits, it would point to a specific file or files that were valid at a given point in time. So we can use this information to check how our data looked like at a specific point in time. So for example, we modified this row with ID 1234. We changed its first name from something to Andrew. And just looking at the history of our table, we did it at this point in time. So let me just comment this part of the query and let's execute it. And we can see that the currently first name of our row is set to Andrew, because that's the current state of our data. But let's say that we want to check how it looked like before our change. So let's grab this timestamp and see how this row looked like at this moment in time. So let me execute it. And here you can see that the first name back then was set to Bambi. So we can time travel. We can see how the data looked like in the past, just by using this timestamp as of specific date syntax. Now, if you don't want to use timestamp, well, we can use versions, right? And again, versions you can see in our history. So this is version 2, version 1, version 0, and we can just use those version numbers. So let's say we can check how this row looked like at version number 1. That was Bambi, because in the version number 2 it was changed to Andrew. And again, this time traveling feature is again super cool because it allows us to see and compare changes we made to our data. But please be aware that it is not meant to replace backups. No. It is also not meant to be stored forever. So if in our requirements we know that actually we would have to record various versions of our rows, of our tables, then we would have to implement some modeling techniques like slowly changing dimensions that we'll cover in future episodes. But this time traveling features is still very useful. It might help us to implement these slowly changing dimensions. Also, it might be very useful if accidentally we messed up with our data. If we run a query on production that made update and it shouldn't be executed there. It happens, right? And by using those time traveling capabilities, you can very easily revert the state of our data to some previous version, just to roll back the changes that were made by accident. Alright, so let's get back to our whiteboard and let's continue listing the cool features of Delta. So the next nice thing we have is vacuuming operation. So if we take a look at our data, you should see that we've got, well, right now we've got 5 files with data, 5 Parquet files. Each of them has some size, so we are paying for this storage. And maybe we don't want to keep all versions of our data because maybe we don't need them. So we would like to remove the ones that are no longer used, that are no longer referenced in the current version of our data. Secondly, there might be cases when our transaction failed in the middle. So we might end up with some additional files, like here, that are actually not being used by any version of our data. But they take space, we pay for them, for the storage, and we would like to remove them. And vacuum operation is just for this. So it allows us to remove files that we no longer need. So for example, it would remove uncommitted files. So it would just clean it up. it would remove files that we no longer need, and we don't want to pay for them. But here we have an impact on deciding which files we actually need, or for how long we want to store our data, our historical versions. And by default, Delta Lake stores historical files for 7 days. It can be adjusted, and after 7 days, if we run a vacuum operation, then older versions of our files would be removed. And please be aware that if we execute this vacuum command and if we remove those old Parquet files, old data files, then it would impact our possibilities to time travel. Simply, if there are no data files from given point in time, then we won't be able to see the state of our data. And this default value of 7 days is quite a good compromise. So it's quite a good option. Now, please be aware that when you're doing this vacuum operation, there might be some other transactions running that actually read those older versions of our data. For example, if someone is doing this time travel query. So just have that in mind. But anyway, vacuum operation is a very cool way to clean up those old versions of the files that we no longer need. Now, yet another cool feature of Delta is schema enforcement. So, schema enforcement. All right, so how does it look like? So let's jump into Databricks. And let's talk about this schema and Parquet and Delta. So you should remember that in case of Parquet, we had this schema saved in metadata, which is very cool. That's something that we don't have in CSV. But unfortunately, it was possible when working with Parquet to accidentally corrupt our data and make changes to our dataset that would violate this schema, because sometimes this schema was not enforced. And let me show you this behavior. So right now I'm switching to Python in Databricks. So that's yet another cool feature of Databricks, that you can use different languages, depend on which one you prefer. And now please don't focus on the syntax of those queries. So basically what I'm doing here is that I created a new dataset as Parquet that has 2 columns, first name and age. And I added just 3 rows to this table. Then in the next command, I'm creating another dataset, but with a different schema. This time it has first name and favorite color columns. I'm adding 2 rows to it, and I'm appending this dataset to the one that we created previously. So we would have 2 datasets with different schema that we want to combine. And let me execute it. And it succeeded. And unfortunately, that's the case that might happen with Parquet, that it might not enforce the schema, and as a result, we have our table with 2 columns, first name and favorite color. So our age column that was present in the first dataset is not visible here. So probably we corrupted our data we messed up, and that's a problem, because sometimes this schema is not enforced for Parquet, which is very bad. So we have the schema in Parquet file metadata, but it might not be enforced. So Parquet doesn't do a very good job at enforcing the schema. Sometimes it does, but there are cases where it doesn't. In case of Delta, that's a completely different story, because here this schema is always enforced. So let's do something similar, but this time let's save our data as Delta format. So again, we start with this first data set, which has two columns, first name and age. And then we try to append a second data set with a different schema and see what happens. And actually, we can see that it didn't succeed. It failed with an error that schema mismatch was detected, which is great because it gives us information that something is wrong. Maybe in our ETL process, we read maybe, let's say, CSV file in an incorrect way, and some columns were just incorrectly read. And when we want to write this information to existing table, it would corrupt the data. But in case of Delta, it was detected. And we can clearly see that we have different schemas for our two data sets. The first one has first name and age. The second one has, again, first name, but also has a favorite color. So these are different schemas. So for Delta, it works very well. So Delta is enforcing the schema. So you should see that when we work with Delta, it looks more and more similar to databases. You've got those ACID guarantees. You've got schema enforcement, which is super cool. But that's not it. To make it even more similar to databases, we have, or we can define various checks and constraints. Checks and constraints. So for example, let's define a constraint. So I'm using, again, SQL syntax. Let's revisit our people table that we created previously. And you should remember that this people table, it contains this gender column. And here I'm adding a check, a constraint, that checks whether values in this gender column are either F for female or M for male. So let's execute it. So this constraint has been added to our table definition, to our Delta definition. And now if I try to make some update that would violate this constraint, it would fail because I tried to set X as a gender, and Delta detected that actually it would violate the constraint that was defined, and the operation would simply fail. So again, we've got this nice enforcement of our data, something very similar to what we have in regular databases. And that was one of the issues with those early adoptions of data lakes, that users expected it to behave similar to databases, but it didn't. It didn't have those various guarantees, various functionalities. And now, with Delta Lake, we finally have them. All right, so let's move on. So we know that Delta can enforce the schema, and it can detect cases when something doesn't match our schema. But sometimes we want to make changes to our schema because data changes over time. Business might change, our source data might change. And maybe there's a new column that we would like to add to our delta tables. And when we have this schema enforcement enabled, it's not possible because it would detect two different schemas. And to handle that, we've got schema evolution capabilities. Schema evolution. So how does it work? So this time we have to explicitly tell Delta that we want to merge the schema, that we are aware that there might be some differences between our datasets. And here we do it by using this merge schema option set to true. And that's the same case, the same query that failed previously, as we are adding this dataset with first name and favorite color columns to a dataset that had age as a column instead of favorite color. Previously it failed, but now when we explicitly instructed Delta to merge our schemas, it succeeded, and it gracefully merged those two datasets. And as a result, we have a table, Delta table, with 3 columns. First name that was available in both datasets, age from the first dataset, and favorite color from the second one. And you can see that the various values for datasets in the case of which given column didn't exist was set to null. But basically that's how we can merge our schemas. That's how we can evolve our data. But that's something we have to do explicitly. All right, let's move on with cool features of Delta Lake. We've got support for merge command. And again, that's something that we had in databases for a very long time. In case of Delta, it is also possible. So how does it work? So basically, let's assume that we've got some new data. This is a table with some new data that we ingested that has like 4 columns, like ID with values 1, 2, and so on. And let's say that we also have a table that we already maintain in our solution. So this is our existing data that was ingested in the past. And again, this table has the same 4 columns with ID column and with some other ones. And let's say that we have values 3, 1, 3, 5, and 7. And what we would like to do is to get the newest extract, this blue new data, and merge it with existing data in a proper way. So we would define it using merge command, and we would instruct Delta to, let's say, try to match our tables based on ID column, because let's say that's a column that stores identifiers of our rows. And if those IDs match on both sides, like for ID number 1, we would like to update this row. So take the newest version that we just retrieved in a new data and use it to update existing data. But when there is no match, so we don't have this row with ID equal to 2, well, that's a new row that we would like to insert to our table. And the merge command, it allows us to do it in a very simple and elegant way. And yes, that's possible when we use Delta. All right, let's move on. Yet another cool feature of Delta is that we can optimize it. So there is this optimize command and the order. All right. So basically, when we work with Delta, we might end up with multiple small files. And in general, it's faster to work on bigger files than on small ones due to some overhead related to reading all these files. And if you would like to grab those small files and consolidate them into bigger ones, that's the optimize command we could use. It would do exactly this. It would just combine various small files into bigger ones, which would make our queries faster. And now, when we execute this optimize command, we can optionally use the ordering, which is a fancy name of deciding how we would like our data to be physically ordered or stored in our files. So you should remember that at the beginning of this session, I executed two update statements. One that required two files to be rewritten because Databricks knew based on transaction log that it has to read two files to find all the data. And there was also a second update query, in case of which only a single file had to be updated. And it was because in transaction log, we had these min and max values based on which query engine knew which files it can skip when performing given operation. And the ordering is just a way we can instruct Databricks or Delta to collocate our data based on some columns. So for example, we could instruct it to order rows in our files based on a country column. So then if we execute some queries that use country as a predicate, then most likely the query engine would have to read one, maybe two files to get all data with specific value of country. And the last thing I would like to talk today about Delta files is that, well, it allows for unified batch and streaming. Batch and streaming. I know we didn't cover streaming yet. We'll get back to it in the future. But basically, with Delta, we can use the same tables, the same Delta tables for batch and streaming processing, which is a great thing because it allows us to reuse the code we wrote for batch processing for streaming. And I know at this moment it might not be clear enough, but we'll get back to it. For now, please just remember that we've got this unification when it comes to Delta files. All right, and that was a brief introduction to Delta. And I hope that you can see now that this is the ultimate storage format that we want to use in our data lakes, because it brings a reliability to our data and a lot of features that we didn't have previously when working with CSVs or Parquet. And that's it. I hope it was useful. So thanks for today and see you soon. Take care.